Good afternoon, class. We are looking at chapter 3 derivatives. Here, section 3.5, the chain rule. So we covered the derivatives and rates of change, derivatives as a function, basic differentiation formulas, the product and quotient rules, and now the chain rule. Again, reminding you of the difference quotient, definition of differentiation for a specific point, a general case, various formulas that you've seen from the basics to exponentials to sine, cosine, power rule, and otherwise, to the product rule, the quotient rule. And now we are adding the chain rule, y equals f of g or f of g of x, which is the composite function. Its derivative is f prime of g of x times g prime of x. And the Leibniz's notation, dy dx is dy du, du dx. Let's get this started with basics. 3.5, the chain rule definition. The composed function f of g, the composition of f and g, is defined as f of g equals f of g of x. Remind you of something from algebra. A warm-up example, if f of x is x cubed and g of x is 1 plus x squared, then f of g or f of g of x means replace the x with the g function 1 plus x squared, which results in 1 plus x squared quantity cubed, and you don't have to raise this to the third power. G of f of x equals g of f of x. That means g of x cubed. That means replace the x with x cubed in the g function. And in this case, you have to raise it to the power of 2 because it's easy to do that. You get 1 plus x to the power of 6. And clearly, f of g and g of f are two different functions. The only time the two are equal, if the two functions are inverse functions. So recall f of f inverse equals f inverse of f equals x. So it only works when the two functions are inverse of each other. So how would you differentiate some composite functions such as y equals square root of 10x plus 5 or 10x squared minus 1 to the power of 2? We use the chain rule. So what is the chain rule? If g is differentiable at x and f is differentiable at g of x, then the composite function f of g of x is differentiable at x, and we write d dx, which is the differentiation operation of f of g of x, is f prime of g of x times g prime of x. Or in Leibniz notation, if y is a function of u, f of u, and u is a function of x, g of x, dy dx is dy du times du dx. If you treat this as a fraction, you see that in essence they cancel each other, dy dx, but that's not a fraction. In other words, if capital F represents f of g of x, then capital F prime, which is the derivative of that, would be f prime of g of x times g prime of x. In the case of a power rule, we know that the derivative of x to the power of n is nx to the power of n minus 1. Let's apply that as a extended power rule to a function g of x to the power of n. The way it works, you have the n. Remember, over here we have x to the power of n minus 1. So that gives rise to g of x to the power of n minus 1. And I'm going to go back to this and remind you what happens here is that the derivative of x is 1. We don't have to write it. But now the derivative of g of x is not 1, and we have to write it times g prime of x. The following trigonometric functions help us understand the concept. When you're looking at trigonometric functions, sinusoidal functions in particular, the way you want to differentiate first, start with the name sine and pause. You know the derivative of sine is cosine. And none of the trigonometric functions have any meaning without their argument. So you must have some sort of an argument, and you have to use the same argument. And because the argument is a function of x rather than just being x itself, by the chain rule, you multiply by its derivative, which is 2, you rewrite it. Same thing happens here. Y equals sine, y equals cosine. You have to use some argument, which means the same argument. The derivative of x squared is 2x. You put that in front. Now, for the last one, you should recognize this as sine x to the power of 2. Therefore, y is 2 times sine x to the power of 2 minus 1, which makes it 1. And now times the derivative of the inside, cosine x, and the final answer is y prime is 2 sine x cosine x. Now, example 1, differentiate let y be u to the power of 5 or f of u, and u be 10x cubed plus 2 or g of x, and we are going to do this 2 different ways. Leibniz's notation says dy dx is dy du times du dx, which means if you look at this concept, your independent variable is u. So right here, you simply write 5u to the power of du dx. Your independent variable is x, and to differentiate the u with respect to x is simply 30x squared. You're practically done. However, replace the u with 10x cubed plus 2. Write the 30x squared next to it. Put that in front, and you get the final answer. 150x squared times 10x cubed plus 2 to the power of 4 as the final answer. Now, this is easy enough, so we can calculate their composite function. F of g is f of g, which is 10x cubed plus 2, which simply put means 10x cubed plus 2 to the power of 5. And as it was mentioned, f of g prime means f prime of g of x times g prime of x. In essence, you're using the extended power rule. First, you need 5. Then the same thing to the power of 5 minus 1 over 4. So the exponent 5 has gone down by 1 to number 4. And by the extended power rule or the chain rule, the derivative of the inside, which is 30x squared. And now, again, you put these two together, and you get the same answer as before. And as I said, in this case, it really makes no difference which methodology you use. In some cases, one may be easier than the other. So I highly recommend you learn both of them. So y equals 10x squared minus 1 to the power of 50. We are going to differentiate this, and we are going to use the extended power rule, starting with n, which is 50. Times the function g of x, that means the parentheses to the power of n minus 1. 50 minus 1 or 49. And now we need g prime, the derivative of the inside 20x. We are done. We just multiply these two and we get 1000x. We put it in front times 10x squared minus 9 to the power of 49. So it's pretty straightforward. We're going to continue with more examples. So we are going to rewrite this so it becomes available for the extended power rule. We raise it to the power of 1/2 first. And now the extended power rule tells us we need n, which is 1/2. Then we need the same function to the power of n minus 1. 1/2 minus 1 is negative 1/2. So we write 10x plus 5 to the power of 1/2 minus 1. So again, this, everybody is this number minus 1. And finally, we need the derivative of the inside, which is simply 10. As you can see, 1/2 and 10, their product is 5. This goes down with the exponent positive 1/2, which becomes the square root. So you put it back in the same format. One more time. 1/2 times 10 is 5. This goes down, becomes the same thing, positive 1/2, and that means square root of 10x plus 1. What happens here? First, you have a multiplier 5, a coefficient 5. You just don't do anything. You keep that. So what happens next? You just work on this part using the extended power. So to work on this one, you need n or 4. Then you need the same function to the power of 4 minus 1. That means 3x minus 2 cubed. And finally, you need g prime, the derivative of the inside, which is simply 3. And we're done with calculus. The final answer is our algebraic technique, 5 times 4 times 3 is 60. We put it in front, and we are done. All right, what about the exponential functions? Reminding you the derivative of e to the power of x is itself. Reminding you, if you have a composite function, you deal with the chain rule and the derivative becomes f prime of g of x times g prime of x. So if the exponent is no longer just x, but rather g of x, then you have the same function times its derivative g prime of x. And if it happened to be e to the power of kx is the same e to the power of kx times the derivative of the exponent, which is simply k, and you put it in front. So with that being the case, this becomes itself. So anytime you see an exponential, just write it, no questions asked. Then the exponent is a function of x. You need its derivative, and you put the 10 in front, in case you want to do it in 2 steps. In this case, the answer is again itself, because you're dealing with an exponential function. Just write the function times the derivative of its exponent, simply put 2t, and that comes in front. Y prime is 2t e to the power of t squared. You can work on this function as it's given. However, if you notice, it means e to the power of 2t because you can multiply the exponent, makes it easier. Y prime is itself because it's exponential function times the derivative of the exponent 2, which you put it in front. You make it y prime equals 2 e to the power of 2t, and you're done. What about this function? Y equals 5x times 3x minus 2 to the power of 4. You have f times g, which requires the product rule in conjunction with the chain rule, more specifically, the extended power. So f prime g plus g prime f, everybody. F prime is 5 times g, just write the function, plus g prime f. Now g prime f, we are going to use the extended power rule. So this one becomes plus n, which is 4, g of x to the power of n minus 1, which is 3x minus 2 cubed, times g prime, the derivative of the inside is 3. And that is done. Go back to your product rule, g prime f, 5x, and I'm going to write at top of it so it becomes clear as to what we just did. And this means f prime g plus g prime f. Okay. And we are going to, and we're done right here. We are done with calculus, everybody. End of calculus. Now the rest will be algebraic techniques. So what do we do next? Well, first and foremost, we put this together as 4 times 3 times 5, 60x in front of it. So this piece remains unchanged. This piece, we write it as 60x, 3x minus 2 cubed. And we notice 3x minus 2 is in common. So we use the smaller exponent, namely cube. 60 and 5, they have 5 in common. So the GCF is 5 times 3x minus 2 cubed. That's the GCF, everybody. The greatest common factor between these two. So when you divide this one by this one, it just gives you 3x minus 2 to the power of 1, or simply 3x minus 2. When you divide this one by this one, this completely goes away. 60x divided by 5 is 12x. So this is not changing, but these two add up to 15x, and the final answer is y prime equals 5 times 3x minus 2 cubed times 15x minus 2. That would be the final answer, everybody. Now, what I want to mention is that, as you can see, number 5 just is a coefficient and remains. Therefore, we could have done it this way. Putting a bracket around it. And finish this one, keep the 5 in front. Now, in this case, it makes no difference. But the more complicated this number, the more involved, the better that method. For example, if it's 5,000, definitely you don't want to carry it. You just want to keep it as a common factor, or if it's a fraction, or if it's a decimal. So be careful with that. So if you go with this route, 5 remains. Now this time is 1, the derivative. See over here, the derivative of 5x was 5. Now it's 1 times 3x minus 2 to the power 4. So the change is the 5 changes to 1. Then the next part, this repeats. This one repeats. Instead of 5x, you just multiply it by x. So if you can see, just we change the 5x to x. The point being, this 5 can be taken out as a common factor. Now, which method is better? You make a decision, but understand for this one really makes no difference. Okay? But it could make a difference if this number is involved. What about this function? You always want to stick with the easy way out. Anytime you have a fractional format where the numerator is a number, in this case, actually, it's a rational function, but it doesn't have to be a rational function. If it's a fractional format, most of the time, it's easier just bring it up as long as it's some sort of algebraic expression and deal with it that way. Now use the extended power rule, which says n, so minus 4. G of x to the power of n minus 1, this one to the power of minus 5, because when you subtract 1 from negative 4, you get negative 5. And finally, the derivative of the inside, which is 14x minus 1. And again, we're done with calculus. Notice this one has exponent negative, so you put it down with a positive exponent. I'm talking about exponential rules, more specifically, negative exponential rules. Whereas in this case, we have to continue with the quotient rule, everybody. So I'm going to write f over g. So a huge fraction bar, y prime equals f prime, which is 1, times g, just write this, minus g prime. So the derivative of this requires the extended power rule, 4 times g of x to the power of n minus 1, 2x minus 1 to the power of 4 minus 1, which makes it 3. And then the derivative of the inside, 2x minus 1 is 2. And going back to the quotient rule, g prime f, which is x. Now the bottom is g squared. This one, you square it, all you have to do, exponent becomes 4 times 2, 8. So what you are looking at, everybody, just quickly to write that, this is f prime g minus, this entire thing is g prime f. And we have to simplify the numerator. We notice 2x minus 1 is in common. This has exponent 4. This has exponent 3. So the GCF would be 2x minus 1 cubed. So if 2x minus 1 is cubed is in common, you divide this one by this one and you get 2x minus 1. And you divide this one by this one, this goes away, you get minus 4 times 2 times x, which is minus 8x. 2x minus 1 to the power of 8, 2x minus 1 to the power of 3. This goes away and this changes to 8 minus 3, which is 5. And these two add up to negative 6x. So the final answer is y prime equals minus 6x minus 1 over 2x minus 1 to the power of 5. Again, we notice we have a numerator which is a number, then we can take the denominator and make it to the power of 1/2, bring it up, becomes negative 1/2. I hope nobody has any problem with that. We are combining this one and this. In essence, this one. So now we use the extended power rule and it starts with 4, nothing changes. Now we work on this. N, which is negative 1/2. G of x, which is x squared plus 3 to the power of n minus 1. Subtract 1 from negative 1/2, you get negative 3/2. In other words, negative 1/2 minus 1 is 3/2. Finally, g prime, the derivative of the inside is 2x. And again, I put an asterisk next to it because I want to emphasize that we are done with calculus, everybody. And so we continue working on it algebraically to finish the job. 4 times negative 1/2, negative 2 times 2x is negative 4x. We put it in front. This doesn't change. So this remains in the numerator, this goes down, and the exponent becomes positive. And you rewrite it in the same format. You know that the square root x squared plus 3 to the power 1/2 is the square root of x squared plus 3, so it's to the third power. And that's the final answer, everybody. Well, as I mentioned, whenever we deal with trigonometric functions, the best course of action to just do the following class. Read cosine and stop. Pause. You know the derivative of sine is cosine, the derivative of cosine is minus sine. Just write minus sine. But it's meaningless without its argument. So what do you use? You use the same argument. So without that, it has no meaning. And then by the chain rule, the derivative of this piece, which is 12t cubed, and you bring it forward, you make it y prime equals negative 12t cubed sine of 3t to the power of 4. So I want to remind you the derivative of sine is cosine. d dx of sine u is cosine u du dx. The dx of sine of gx is cosine of gx g prime of x. This is by the chain rule. For cosine, the derivative is negative sine. d dx of cosine u is minus sine u du dx. So this is the du dx, in this case du dt. d dx of cosine gx is minus sine of gx g prime of x. So we are looking at dy prime here is d dt because the independent variable is t. You want to differentiate this, and there is no reason to use the quotient rule. You notice that if you divide these two, you get x. In other words, make up two fractions. And these two will give us 4. So we have x plus 4 to the power of 6. And now we can use the extended power rule on that. The number n6 sits in front. G of x meaning the same thing to the power of n minus 1, 5. And then the derivative of the inside, although it's 1, I like to write it because sometimes it's not. And of course, we are done. 6 times x plus 4 to the power of 5. However, in this case, we must use the extended power rule in conjunction with the quotient rule. Therefore, n, which is 5, g of x, which is this function, to the power of 4. And now we're going to differentiate this using the quotient rule, and I'm going to call this f over g using this one, everybody. So what we get here, f prime g minus g prime f over g squared. F prime is 2 times g, which is x minus 8. Minus g prime, the derivative of the bottom is 1. Times f, which is 2x plus 3. G, x minus 8 squared. And I'm going to put the asterisk next to it. Done with calculus. Now the rest of it is algebra and algebraic techniques to simplify. Okay, everybody? So 2x minus 16 minus 2x minus 3. 2x cancels out the negative 2x, and we get negative 90. Now, if you can see what's happening, you can avoid the next step. If not, it is helpful to notice this means the top and the bottom are both being raised to the power of 4. So I'm going to write this as numerator to the power of 4, denominator to the power of 4, and this one is simply negative 19 over x minus 8 quantity squared. So the reason I write it, because I want to make sure that you see the denominator is x minus 8 to the power of 4, and then x minus 8 to the power of 2. The result is x minus 8 to the power of 4 plus 2, which is 6. And the top is this number, this function, and this. So the product of these two is negative 95. So finally, we get negative 95, 2x plus 3 to the power of 4, over x minus 8 to the power of 4 plus 2, or 6. And that's the final answer, everybody. What about the exponential functions? Remember, the derivative of exponential function is always itself. So we're going to start with that. And of course, then we pay attention to the chain rule. So in this case, I'm going to write e to the power of 5t. So any exponential function, just quickly write that. By the chain rule, the derivative of 5t is 5, put it in front, and you're done. Part B, the answer is itself, e to the power of tan x, times the derivative of tan x, which is secant squared, and you're done. Y prime is e to the power of tan x, secant squared, x. The last one, just to make sure we understand that this means 2/3 x, I rewrite it just for that reason. You don't have to if you see that. So y prime is the same thing. By the chain rule, the derivative of the exponent, and you put that in front. Y prime is 2/3 e to the power of 2x over 3 or 2/3 x. What about y to the power of 3? Y equals 3 to the power of x. When the base is e, we know the derivative of e to the power of x is itself, e to the power of kx is itself times k, e to the power of g of x is itself times g prime. We have no idea what is the derivative of 3 to the power of x is yet. So what is the derivative of b to the power of x? We use the logarithmic property that says ln of e to the power of x is x, or e to the power of ln x is x, and we're going to use this property to write b, the base, as e to the power of ln b. The reason we do that, because we know what's the derivative when the base is e. So we are going to replace the b with e to the power of ln b. And it's important to understand ln b is a number like 5. So what you're looking at is e to the power of ln b times x. Please understand it's identical to e to the power of kx, essentially because ln b is a number. So the derivative works the same way. So the derivative is the same thing times ln b. But we know that e to the power of ln b was b. We are going to put this back and we make it b to the power of x. So b to the power of x, which means if you want to differentiate this, first you write itself, then you look at the base. If the base is e, so be it. If not, by the logarithmic property, you need natural log of that, and now it's done. You can rewrite it or leave it. Either way is fine by getting rid of the raised dot. So it's very straightforward. Any exponential, the answer is itself. If the base is e, fine. If not, you need a natural log by the chain rule. How about this one? Well, in addition to what we have, we are adding the chain rule. So if we have b to the power of f of x, y prime is the same thing because it's an exponential. ln b because the base is not e, and f prime by the chain rule. So the answer is itself because it's an exponential. ln2 because the base is not e. The exponent gives you 7. You rewrite it and you're done. So in short, anytime you see the exponential, first just put the answer as the exponential, then look at the base. The base is e, so be it. If not, you need a natural log. And then you look at the exponent. If you need to use the chain rule to multiply it by g prime of x, by all means. Here's the derivative applications. Example 1, after t weeks, the number of people using a Newtron rapid transit system was approximated by n of t equals 6t squared plus 500t plus 8,000. At what rate was the use of the system changing with respect to time 8 weeks after 8 weeks? And that means the moment you see rate and 1 point in time, differentiation n prime of t. So that means 12t plus 500. At what point? T is 8. 12 times 8 is 96, plus 500 is 596. Y people per week. This is dn dt. The change in n, the number of people. over the change in time in weeks, people per week. What does it mean? On week 8, the number of people using the transit is increasing at the rate of 596 people per week. Why increasing? Because this is a positive value. If it were negative, we would say we would not change anything except this one would change to decreasing.